Hello everybody and welcome to Thermal Physics Lesson 2. Now in the first video we had a look at the three key things that you can see there on the screen. We first looked at internal energy, and remember that internal energy is just the sum of all the kinetic and potential energies of all of the molecules within a system. Next, we looked at the first law of thermodynamics, which really is just the law of conservation of energy, but of course we put an equation on it, and the equation said that delta U, where U is the internal energy, is Q, which is the heat absorbed by the system, minus W, which is the work done by the system. And then finally we looked at Kelvin, the Kelvin scale, and absolute zero. And we said that to go from degrees C to Kelvin, that we just need to add 273.15. Obviously to go the other way, to go from Kelvin to degrees C, we subtract 273.15. Now, of course, the reason for that is that because absolute zero which is obviously defined as 0 on the Kelvin scale, is minus 273.15 degrees C. But remember that the scale division, so the change of 1 Kelvin, is the same as the change in 1 degree C. In this video then, what we're going to start to focus on from the first law of thermodynamics, we're going to have a look at heat. And we're going to have a look at how heat and temperature of a substance are linked together. So in order to look at heat then, firstly, I've brought forward that first law of thermodynamics. Now, I just want to remind us of a couple of things that we said in the last video, and mainly to do with the definition of Q and the sign of Q that we care about. Now, we said that if Q was positive, then that denoted that heat was being absorbed by the system, and if Q was negative, then heat would be released. Now, of course, looking at the equation, if Q is positive, in other words, if we are absorbing heat into the system, then delta U will be positive as well, and the internal energy will increase. Now, of course, if the internal energy increases, then what that's going to do is it's going to cause the temperature of the system, of the substance, to increase as well. Obviously, the same goes the other way around. If Q is negative, then delta U will be negative. The internal energy is decreasing, and therefore the temperature is decreasing as well. Now, normally in everyday speech, the words heat and temperature tend to be synonymous, but really, when we're looking at it, heat is of course a measure of energy, whereas temperature, well, it is its own measure, it's linked to energy, but it is different. Now, what we can see here then is that we're starting to form the idea of a relationship between Q, the heat, and temperature. And what we can do is we can summarise the relationship like this. We can say that delta Q is proportional to delta T. So the amount of heat either absorbed or released. And of course, what the delta Q will do is it will take care of the sign, whether it's positive or negative, within that delta. And that is proportional to the change in temperature. Now, fortunately, it is a nice, simple, linear relationship, but of course, as usual, we want to remove that proportionality sign and we want to replace it with an equal sign and any constants that we care about to turn it into an equation. Now, the two things that we care about when we're looking at heat absorbed or heat released and change in temperature, firstly, we have the mass of the substance. And obviously, if we've got a higher mass, we're going to need more energy, more heat, in order to change its temperature. The second factor in this is the substance itself. And just like with a lot of other things that we study in physics, such as density and resistivity and things like that, there is a constant that is linked to the substance which will feed into the equation. Now, to start to bring this all together then, so that's just bringing everything over from the last screen, delta Q is proportional to delta T, and we've got to do something with the mass and the substance. Now, firstly, hopefully we can see that, as we said before, delta Q is proportional to the mass. So in other words, the more mass we've got, the more energy, the more heat we need to change that temperature. Now, from the substance's point of view, what we need, the constant that we need for the substance is known as the specific heat capacity. And there then is the definition, it's the specific heat capacity is the amount of energy required to raise the temperature of 1 kilogram of a substance by 1 Kelvin. Now, the symbol that we use for specific heat capacity is a lowercase c, unfortunately not to be confused with the speed of light here. And we'll have a look at what the unit of specific heat capacity is in just a moment's time. Bringing this all together, as we said then, we're going to end up with the equation delta Q is equal to, well, obviously we need the mass on that side of the equation to make delta Q proportional to the mass. At that point we can put the constant, the specific heat capacity in, and obviously finally we can put the change in temperature in, and there then is the specific heat capacity equation. Now, to look at the units then, obviously we know that Q is the change in heat, but as we've said all the way through, the unit for that is joules. It is just an energy. M we know is mass, and mass will be measured in kilograms. Delta T is the change in temperature, and we know that temperature is measured in Kelvin. So if we have a look at the specific heat capacity then, so that's the C here, the specific heat capacity. Well, in order to make the units work, well, obviously overall we've got to end up with joules, so we've got to have joules in there somewhere, and then looking at the right hand side we've got to cancel out the kilogram and the Kelvin, so we have kg to the minus 1 and k to the minus 1, and that would be said as joules per kilogram per Kelvin. Now, just before we move on, as a note about change in temperature, obviously the unit that we use, because it is a base unit, is Kelvin. But as we said in the last video, and obviously in the introduction to this one as well, we know by definition that a change in 1 Kelvin is exactly the same as the change in 1 degree C, because the scale divisions in the two scales, in the Kelvin scale and the Celsius scale, are exactly the same. So you, at least when it comes to the specific heat capacity equation, you can get away without having to do that conversion in the first place. So if you're given temperatures in degrees C, you don't, for for this equation have to go through the rigmarole of adding 273.15 every time in order to do it, because the difference between 20 degrees and 30 degrees when it comes to the Celsius scale is exactly the same as what would it be at that? It will be 293.15 and 303.15 on the Kelvin scale, and we still end up with a difference of 10 regardless of which scale we use. So to look at specific heat capacity then, what we said before is that specific heat capacity is a constant for a given substance. So it's in the same kind of vein, as I said, as density, as resistivity and that kind of stuff. So you look at density, if you have 2 blocks of copper, they will have the same density regardless of their shape and size. They'll have the same resistivity regardless of their shape and size, and they'll also have the same specific heat capacity as well. So it is definitely a material constant. One thing just to be careful though about with specific heat capacity is it does depend on the state of matter. Because obviously with the way that the molecules are arranged in the different states of matter, the way that we are going to get energy in to increase the internal energy is going to change depending on that. Now, just to give you an idea of how that works then, let's have a look at water. Now, when water is in its solid form, in other words, it's ice, then the specific heat capacity is 2,100 joules per kilogram per Kelvin. When it is a liquid, so normal water as we would say, then the specific heat capacity is 4,200 joules per kilogram per Kelvin. And when it is a gas, when it's in its vapour form, it will be 2,000 joules per kilogram per Kelvin. So while it's the same substance, we obviously know that water, or obviously from the chemical point of view, is just H2O. Depending on the state of matter, we end up with different specific heat capacities for the same substance. So here is your question for this lesson. A 2.4 kilowatt kettle holds 1.7 kilograms of water. If the water is at 17 degrees Celsius, how long does it take to boil the water in the kettle? And you can see there, state any assumptions that you make in this calculation. So as usual, pause the video at this point, go away and have a go at it, go and get your answer, and then come back when you think you've got that answer. So firstly then, we know that we're doing some water heating, so therefore we're going to need the specific heat capacity equation. Delta Q is equal to mc delta T. But of course what you can see as well is that instead of energy, we've been given power. So we've got a 2.4 kilowatt kettle. Now, of course, the equation for power, rate at which energy is transferred, rate at which work is done. So we know, at least in basic forms, it's P is equal to E over T. Now, what we can do then, delta Q we know is given in joules, and E we know is given in joules as well. So therefore, I'm just going to rearrange, and instead of P is equal to E over T, I'm going to say that E is equal to power times time, and then I can equate the two. So delta Q is equal to mc delta T, capital T for temperature there. I can now equate to E is equal to PT, little t for time. So let's do exactly that. So P times T is equal to mc delta T, and as I said, don't get your T's mixed up here. Little t for time, capital T for temperature, and obviously then we're just going to divide both sides by power, and we get time is equal to MC delta T divided by P. At this point then we can start to plug in some numbers. So the mass of the water is 1.7 kilograms, multiplied by the specific heat capacity, 4,200, and the change in temperature, well again let's do this properly with change, so it's always final minus initial, so it's 100 minus 17. Now we know that that's going to be 83 degrees as a change in temperature, 83 Kelvin really is a change in temperature there. But again, I'm just showing you how to do that absolutely properly, just getting you in the good habits with those deltas and making sure that we do final minus initial. Anyway, we divide by the power, so it's 2.4 kilowatts, 2,400 watts. Now when we plug all of that in, the final answer we get is 247 seconds. Now that, when you convert it, is 4 minutes and 7 seconds, which to be honest for boiling a kettle seems, it's a little bit quick, but it does seem like a reasonable time. Now for the assumptions, the way I see this, I have made two assumptions in this question. The first assumption is here, and we've assumed that the boiling point of water is 100 degrees C. Now of course that's the sort of standard value that we take, but of course that doesn't take into account any change in atmospheric pressure, doesn't take into account altitude and all this kind of stuff. It's just a sort of recognised version, recognised number for the boiling point of water. The second assumption is really the key assumption. And what we're saying is that we've got no energy lost from the system at all. Now in reality we know that that isn't strictly true, because of course if you do put water into a kettle, well when the water heats up, that heat is conducted through the walls of the kettle and then it will be radiated into the room, and therefore we are going to get energy losses. So that's the second assumption made, is that no energy is lost from the system. Now as I said, realistically 4 minutes and 7 seconds is probably a little bit quick. The kettle probably takes about 5 minutes to boil properly, and that's because obviously in our calculations it's that second assumption that we haven't taken into account any energy losses from the system. So to summarise then, in this video we've looked at specific heat capacity, and firstly there on the right hand side is the definition. So the specific heat capacity is the amount of energy required to raise the temperature of 1 kilogram of a substance by 1 Kelvin. And from that we have the equation delta Q is equal to MC delta T, where of course C is the specific heat capacity and takes the units joules per kilogram per Kelvin. So that's it for this video. As usual, I hope you've enjoyed that and got something useful out of it, and thanks for watching, and I'll see you in the next video.